Hello everyone, my name is Arpit Narichania and I'm excited to present DataCockpit, a toolkit for data lake navigation and monitoring utilizing quality and usage information. This work was done in collaboration with Surya Chakraborty, Shivam Agarwal, Atanu Sinha, Ryan Rossi, Fan Du, Jane Hofswell, Shonan Guo, Uni Ko, Alex Endert, and Shamkant Nawathe. We are all researchers from Adobe Research and Georgia Institute of Technology. Today, organizations often amass or dump their data into centralized repositories called data lakes and perform analytics only much later. Unfortunately, the inherent data overload due to this load first philosophy poses several challenges such as navigating the data lake, discovering relevant data, flagging irrelevant data, and monitoring the health of data. Also, no single user knows about all the datasets, let alone what each one contains. Existing proprietary as well as open source tools provide data profile, quality, and lineage information for data observability, monitoring, and pipeline optimization purposes. We explore solving these problems by modeling data usage. A notable aspect of data lakes is their centralized nature that enables a large number of users to access a large variety of datasets. These access or usage logs can provide deep insights into what data is being used and how. We present DataCockpit, a Python toolkit that takes as input a series of database connections and their corresponding query logs, and computes data usage information such as who used the data in what applications and when. And it also computes data quality information, for example, if there are missing values or errors. Both quality and usage information is stored back into the data lake for future access. We define data usage as the historical utilization characteristics of data across other users, and data quality as the validity and appropriateness of data required to perform certain analytics. Data usage. Consider a data lake as a repository of multiple relational databases along with their query logs. Each query log consists of an ID, the execution timestamp, the SQL query, the database, the application, and the user, similar to the MySQL general query log. For each query log, DataCockpit processes the executed SQL query and extracts the datasets used from the from and join clauses, the attributes from the select, update, where, group by, order by, and having clauses, and records from the where and having clauses. This, together with other information such as the user, application, and timestamp, is stored in a new table. This table can be further aggregated at an attribute level. For example, the total number of queries it has been used in, the unique number of users who accessed it, in unique applications, and the most recent timestamp of use. In addition, the information can also be grouped by timestamp into temporal periods, for example, monthly. Next, data quality. DataCockpit computes several data quality metrics for attributes as well as records. Let's take a look. First, attribute completeness. We define attribute completeness as the percentage of non-missing values for each attribute. Consider this table configuration with 5 attributes and 4 records. There are certain missing values in orange and the rest non-missing values in purple. Now, for each attribute, the percentage of non-missing values are the percentage of purple cells along the vertical dimension, which turns out to be 100, 75, 50, 25, and 0 respectively. DataCockpit computes these using a single SQL command. Next, record completeness. We define record completeness as the percentage of non-missing values for each record. Consider the same table configuration with 5 attributes and 4 records with missing values. For each record, the percentage of non-missing values is the percentage of purple cells along the horizontal dimension, which turns out to be 80, 20, 60, and 40 respectively. Like attributes, DataCockpit computes these scores using a SQL command as well. Next, attribute correctness. We define attribute correctness as the percentage of correct values for each attribute. Consider a new table configuration with 5 attributes and 4 records, but this time with correct values in purple and certain incorrect values in orange. For each attribute, the percentage of correct values is the percentage of purple cells along the vertical dimension, which turns out to be 100, 100, 50, 25, and 100 respectively. Given the criteria for correctness, DataCockpit computes these scores using a SQL command. Next, record correctness. We define record correctness as the percentage of correct values for each record. Consider the same table configuration with 5 attributes and 4 records and certain incorrect records. This time for each record, the percentage of correct values is the percentage of purple cells along the horizontal dimension, which turns out to be 100, 60, 80, and 60 respectively. Like attributes, given the criteria for correctness, DataCockpit computes these scores using a SQL command. Next, attribute objectivity. We define attribute objectivity as the extent to which values conform to a target distribution, and it is computed for each attribute. Consider a new table configuration with 5 attributes and 4 records, but this time with a gender attribute A2 that has 3 males and 1 female. If this table column is supposed to have an equal distribution of males and females, that is, if M's must equal F's, then the gender attribute or A2 is considered objective. In this case, it is not, hence objectivity is 0. Given the criteria for objectivity, DataCockpit computes these scores using a SQL command. Note that objectivity is not applicable at a record level. Next, attribute uniqueness. Uniqueness is the number of unique values for each attribute, or in other words, its cardinality. Consider the table configuration with each color representing a unique value. So for each attribute, the number of unique values is the number of colors along the vertical dimension, which turns out to be 1, 2, 4, and so on. DataCockpit computes uniqueness using a SQL query as well. Finally, record freshness. Freshness determines how fresh a record is. That is, has it been ingested in a timely manner or not? Consider the table configuration with purple records as ingested in time and the orange record ingested late. DataCockpit computes freshness by comparing each record's ingestion date with a predetermined reference date and a freshness threshold, or a unit of what is considered late, all using a SQL query. In this way, DataCockpit computes both quality and usage metrics. I would like to note that DataCockpit is actually based on and an extension of DataPilot, a recent system and technique presented at the ACM Chi conference this year. In a gist, DataPilot is a visual data preparation and analysis tool that also computes quality and usage metrics, but for one tabular dataset. A user study to understand how users utilize these metrics to select data subsets and make visualization dashboards showed that DataPilot users selected smaller, more effective subsets with higher quality and usage scores. So we then developed DataCockpit to expand this functionality to multiple relational databases, which is our data lake. Now, how does DataCockpit expand to multiple databases? First, to reiterate, DataCockpit computes quality and usage metrics for each attribute and record, which is normalized to a score between 0 to 100. Then an overall score is derived, which for usage is the max of individual scores. Max because not all data is used across all applications, and several low scores would demotivate the users. For quality, on the other hand, this overall score is the mean of individual scores. And finally, overall scores are aggregated to higher granularities of data. For example, at the data set level, using a weighted average, because some metrics are more important than others. We developed DataCockpit as an open source Python toolkit, wherein users first initialize the toolkit with SQL Alchemy database engines and the respective paths to the usage log files. Next, they compute desired quality and usage information. And finally, they retrieve this computed quality and usage information for use in downstream applications. Using DataCockpit, we developed a visual monitoring tool. Let's check it out. The landing page presents an interactive data table with basic information about all datasets in the data lake. The last two columns correspond to overall quality and usage scores as colored glyphs. Datasets with higher scores are shown in green and lower scores in red. Clicking any row opens a detailed view about that dataset. First, there is basic information about the dataset along with a few sample records as a preview. Second, overall quality and usage scores along with their constituent dimensions are presented as colored glyphs. For example, completeness of the dataset is 70%, and because this value falls in the medium category, it is colored yellow. Third, users can visualize the evolution of quality and usage scores over time. For example, when new dataset batches are ingested and metrics are recompiled. Finally, the quality and usage information for each attribute is presented as a hierarchical tree visualization. This visualization is interactive, providing affordances to pan, zoom, expand, and collapse attribute nodes. Nodes are colored based on attribute level quality scores by default, but can be changed to usage scores as well. Hovering an attribute node shows attribute level quality and usage scores. For example, city has a correctness of 80%. Like the visual monitoring tool, DataCockpit has many applications across different types of users. For example, data and system administrators can efficiently find low quality, low recent usage datasets and mark them for archival or cold storage. They can also monitor shifting trends in the data. For example, age is being queried a lot. Next, experienced end users can reuse tried, tested, and effective attributes from previous analysis and dashboards for future ones. New users can efficiently learn these metrics across all datasets, flattening their learning curve. And finally, developers can create usage and quality powered tracking and monitoring capabilities into their own new tools. Both DataCockpit and the monitoring tool are available as open source software at these given links. Now, what's next for DataCockpit? We plan to support more quality metrics, for example, consistency. Provide advanced analysis, for example, anomaly detection. Design a user interface to make it easy for users to configure thresholds. For example, the criteria for what is considered missing, incorrect, or objective. We want to become privacy friendly by serving user requests as per an organization's data governance policies. And lastly, we want to support additional data sources, for example, JSON-based ones or Parquet. For more information, please check out our GitHub repositories, read our paper, or reach out to us. Thank you.